Hi everyone, Mr. Ford here. I'm going to walk through some of the worksheets in the projectile motion packet. Just for sake of time, I'm going to walk through the setups and leave the numerical calculations for you to look at in Schoology under the homework solutions. So here we go. So we're going to work on worksheet 2. This is to the point where I think we left off that needs some explanation. So here we have kind of our similar marble going off the table problem that we looked at before, just a few other nuances. So the marble that's here is going to eventually reach the edge of the table and then move in its parabolic motion and then hit the floor. So we're asked to figure out where horizontally relative to the edge of the table is it going to reach. So we're looking for this delta x. And again, we can't use this as a triangle because the parabolic motion of the ball does not actually make a triangle. So the little different part of this one is we have these things called photo gates here. Photo gates, just like the word intends, photo meaning light, gate meaning just like a path where you're going through. So we actually have these in the classroom. We don't use them a whole lot because we do have the motion sensors, but before motion sensors, they had these basically beams of light that would go through from one sensor to the other, and you can set this distance, and then what would happen every time the ball goes through each photo gate, you have a time. So you know the time to go through here. So since it's a horizontal table and there's no horizontal forces, when the marble goes down, of course, it's going to increase its velocity. But then when it gets horizontal, it's moving at a constant velocity. So we can use that simple velocity in the x direction is delta x over t. So we're given that it takes 0.2 seconds and the photo gates are 30 centimeters apart. So we have enough information to calculate that. So this is actually how for the projectile motion lab, we could confirm if there was conflicting results with when we shot the ball straight up. We measured the distance and we measured the time and we found those velocities two ways. If we were really off, I could set this up and we could do the same thing with the ball. So our displacement was 30 centimeters, 0.20 seconds, and we get a horizontal velocity of 150 centimeters per second, or 1.50 meters per second. So now we have our horizontal velocity. So let's see, we know that this ramp is 0.92 centimeters above the floor. So we break up our scenario. I always like to make a little table. Let's go green. With my x direction information and my y direction information. So my answer is going to come from my x direction because that's what we're looking for. How far horizontally from the edge of the table is the ball going to land? So that's going to be our velocity in x direction, which we have, times the time. So we just have to figure out from the vertical part of the problem, how long is it going to take the ball to fall? Because the time is the same for both x and y directions. So vertically, we know the delta x, or delta y rather, is going to be negative 9 point, or let's see, point, let's look up here. I made a mistake here, so this should be 0.92. 0.92 meters, not centimeters. And I'm going to convert that to meters just simply because we know acceleration is going to be 9.8 meters per second squared, so might as well convert any centimeter that we have into meters. We know our initial y velocity is 0 because it's moving horizontally just in the beginning, and then it will start from essentially rest as we're falling, or you can look at it as just falling straight down from this moment. So whatever time it takes to fall straight down is the same it has to go outward. Let's see. Oop, filled in wrong information here. So again, I got kind of distracted with my previous mistakes. So our 0.92 meters displacement, our acceleration, negative 9.8. And the equation that 9 times out of 10 that you'll be using is this one. Making sure that you show all your work and you show all your units so that if there is a little mistake, we can track our work and you're showing what you understand. So even if it's homework, you want to get into a habit of showing that. Like you can just simply, you saw me make that little mistake, and then as I was going to fill out the rest of my givens, I found my error. Just simple mistakes there. And that was actually not purposeful. This value drops off as 0 because our initial velocity is 0, so no really need to put that in there. And that way it does not need us to factor a quadratic. So we could solve for our time, making sure to take the square root when we finish out our algebra, take that over, plug that in, and we would get our delta x. So if you need to see the final numbers and calculations, refer to Schoology under the homework solutions. Number 3, we're looking at the same ball released from the same ramp. And we know that where the ball is going to land. So now we're working backwards to figure out how fast was the ball going. So this is the opposite of what we did. So before, we got our answer from our x direction side. Which we're still going to do, but it's a little bit different. We're looking for velocities, not displacements in this case. So we're going to know that it takes 0.25 meters. We're going to be looking for our Vx now. And our time we're going to have to get from our y direction information. So same thing, it's our same height of table. Our y is the same. Actually, I don't need to go through any of this, do I? No, it's still that same time it takes, which was about 0.43 seconds. So we take that time, bring it over here, and we're going to get our Vx. Or I'll go ahead and do this one since it's a little bit backwards. And we get our part A solution of about 0.58 meters per second. So it's back to the initial part. So looking at our photogates. So if we know the speed and we know how far the photogates are apart, we can figure out how long it takes the ball to go through. So it's still looking at our horizontal information, just the next part of our problem, where this is like the photogate one. Where if we simply do it like, I guess I got this way. We know we're 0.30 meters or 30 centimeters apart. Our velocity, we figured out. And we solve for our time, which we would get. So again, the same physics really there. It's just different nuances of the question. All right, so we're going to go ahead and move to worksheet 3. And this packet is a little dated. I don't think I've ever seen this particular movie. But the physics will be the same. So the best thing to do is to draw a picture where we have this bottle falling out of an airplane and it lands on the ground. We know the height of the plane when the bottle was dropped and how far horizontally it went. So I'm gonna go some easy drawing here. So this is how high we are from the ground. Let's see, we're 500 meters up, right? And the trajectory or path that the bottle is going to take is a parabola. So we'll land down here. And this distance was 400 meters. I guess I should draw it like this. And we're really looking to see what velocity it was moving in the x direction to see how fast this plane was flying. And again, this is assuming there's no friction, no air resistance, because we would have to do some other calculations. So same method here, split it up into x and y. What do we know in the x? We know the delta x, 400 meters. We're looking for our velocity in the x direction. So we need to find our time. That's, 9 times out of 10, that's going to be your next step, is figuring out the time. Because we're solving for that. And we can plug in our time after we get it. So in the y direction, we know acceleration, negative 9.8. We know the delta y is in negative 500. And once you start to get comfortable, feel free, since we know that the acceleration is negative, the displacement is negative in this scenario, everything is going down, you can call that positive if you like, if the negatives tend to trip you up sometimes. Let's see, what else do we know? We know our initial y velocity was also 0, so we're going to use that same equation that we did before, where the VIT will drop off as 0. We solve for the t, plug that in over here, and we can solve for Vx. And we know how fast the plane was moving. We don't need to do the motion map. We don't do those. And again, if you need the numbers, refer back to Schoology under the homework folder. This one, let's see. So the real question is, how far from the point of release would the sack of flour be? So we're looking again for that horizontal displacement. No need to graph it out. I don't think here it's mainly looking for a motion map out of you. No need to put it through the scale, as long as you can draw a picture of it. So let's go through and solve this problem. The plane's flying 60 meters per second horizontally at a height of 300, so it's going to move downwards 300 meters when the flour is dropped. How far is it going to go? So again, you should start to see that there is a trend here. solving, plugging everything and solving for that t, bringing it over to here, and we can get our horizontal travel of the sack of flour. Now, the next question is, where will the plane be in relation to the sack as it hits the ground? So this is where the physics gets kind of weird, reality versus, the classroom physics where there is no air resistance. If this is the path, this is just a rough sketch, the path that the sack of flour is going to take, the plane is going to be moving horizontally, right? So if the horizontal velocity of the plane is always 60 meters per second and the horizontal velocity of the sack of flour is 60 meters per second, they're always going to be in the same positions. So if they both started in the same position here, you would have like your plane, P for plane, F for flour. They're always going to be above and below each other. So plane, flour, plane, flour. So they'd be moving horizontally at the same rate. Now, it's a little bit different in reality. If you were in a car and you were not being a nice person to the environment and you threw something out your window, it obviously lands someplace behind where you are because of air resistance. But think how cool this would be if you're traveling in a convertible and you had a tennis ball and you're obviously not driving, maybe you're the passenger, and you threw the ball up in the air. In reality, the ball would land behind the car because the car is moving. You throw the ball straight up, and air resistance has an effect on it, and it obviously goes behind you. But if there was no air resistance, or you're within the car and the top is up, you throw the ball up, it comes straight back down to your hand. So if this question is a little confusing for you, there's a great flipping physics video where the professor, or the teacher rather, does that. He's driving in a car, or he's the passenger in a car, and he has like a slow-mo video of dropping a tennis ball, and you can see the relative positions of both because we can ignore air resistance for a short distance. Okay, so let's see. Number 3. So we have our stone quarry, which is just a big hole, and somebody's standing on the side of it, and they throw a piece of rock over the edge. And we need to figure out how high they were above the water. So again, this is useful to sketch out a picture. It's a weird looking guy. Let's do this a little bit to scale here. And he throws a rock and hits the water. And we know that's 4.5 meters away from the base. And he throws it with a horizontal velocity. This is the rock. 3 meters per second. Again, break up into X and Y. No need to use this chart, but I like to do that because it does give a clear indication of what you're measuring. And that does, even though I put it anyway, I always put like V subscript X. But if we have it in this chart, we don't really need to do it. But I just do it for clarity. So this problem is a little different because we're given everything for the X to find the time, then moving to the Y. So we can plug that in, get our time. We're going to bring that over to this part where we know acceleration. And we know we use that same equation again. Oops. Where this drops off because it's 0. We're going to use that time that we found on the horizontal to find our delta y. And making note that you should get a negative here because our acceleration is negative, so this whole term will be negative. But some of you are saying, well, Mr. Ford, if you square a negative, you get a positive. Again, it's not a number that's negative. It's almost like doing like a negative absolute value of the t, if you will, because we need to look in terms of a direction. Let's see. 4, same thing again. I think by now we get the idea of the setup of everything. So I'm going to leave you to your own for 4, since it is still a horizontal scenario. And I'm going to move to number 5. So now we're looking at non-horizontal motion because it's moving at 50 degrees above the horizontal. So this is where the football is going to be kicked at 50 degrees. So this is our velocity vector, where we're going to break it up into its components, just like the second part of our lab, where this is going to be our Vx, and this is our Viy. We do know the angle. So I'm going to go sine of 50 degrees is going to be my Viy over my hypotenuse, making sure I'm in degree mode. And we get our Viy as about 19, call it 2 meters per second. You can round however you like. And cosine 50 degrees to get our Vx. And I'm going to pause the video there. I do need to come back in a little bit.